Okay, Assalamualaikum warahmatullahi wabarakatuh. My name Ahmad Amirul Ashraf bin Osman. My metric number AE200001. Okay, in this video, I will explain about activity 1, the series of resistive inductive load circuit. Okay, in this simulation, we have a V sine, AC emitter, AC voltmeter, resistor, and inductance. Okay. First, we connect the circuit with the wire, and we put the resistance and inductance in series. Okay. After we put the wait, we make it bigger. Oops. Okay. After we put all the wire connection together, and then we simulate this circuit. For the 860 ohm and 0.4 for inductance, we get a 8.14 milliammeter and 7.07 volts. Okay, so the simulation is success. Okay, that's all from that's all for activity 1. Okay, next is the activity 2 for uh, the parallel resistive inductive load circuit. Okay, this is the simulation of uh, activity 2. We have voltage sign, AC emitter, AC voltmeter, uh, 2 resistor, and 1 inductor. Okay, first we connect the wire for each. Okay, first we connect in parallel. Okay, we put a 210 for R1 resistor 1, 0.4 for inductance, and 1 for another resistor. I put this resistor series with inductance to make a circuit breaker for inductance. Because when I don't put this resistor, the simulation cannot be run. Okay, we test to run the simulation. Okay, and then we get the total current for this parallel circuit is 65.6 milliammeter, and total and voltage for this circuit is 7.07. Okay, when I calculate manually, the answer is almost same with the simulation that I do. So I think the simulation gonna be success. Okay, that's all from me. Thank you.
Okay, hi, Assalamualaikum warahmatullahi wabarakatuh. Uh, my name is Amar Fikri bin Muhammad Naski. My metric number is AE200004. Today I will present about activity 3, which is the series resistive capacitive load circuits. So now, first of all, I would like to explain about the component that we use for this activity. For the power supply is AC, we use AC power supply. And we said the power supply is 10 volt and 50 hertz for the frequency. And for the emitter, we need to change the display range. We set to milliampere, and the resistor and capacitance, we have the different value, which is we have 6 value and we have 6 different circuit. Now we run. Okay, we got all the value. We got all the simulation value. Now we go to the report for activity 3, the series resistive and capacitive load circuit. Okay, here we got the circuits from the purchase from the software. So the value for the different value for the different 6 different circuits is uh, different value for resistor and capacitor. This is the value for resistor and capacitor, which is we have 6 different value, and the value that we got from the simulation, which is V load, and we got the I here. Okay, here we got the value from the circuit. Okay, now what we need to find is we need to find the I. Okay, how we want to find the I? We can use this formula, which is we need to find the Z first. For Z, we use the formula Z equal to R plus 1 over JWC, which is W is to pi F, which is the frequency is 50 Hertz, like we said in the B supply. Okay, so after we get the Z value, we need to find the XC, which is we can use this formula. XC equal to 1 over 2 pi FC. So if we get the value for XZ and the XC and the Z, so we can find the value for I. So we can use the formula, which is I equal to V supply over Z. V supply, we have set 10 volt from the software. So 10 over Z here. Then we get the value for I. Okay. So what we can conclude from activity 3, based on the calculation and simulation result obtained from activity 3 in RC series, from the table 8.3 shows the current value for simulation value and calculated value almost have the same value, which is almost has the same value. So capacitance value was directly proportional with the value of current, because the more value added to capacitance, the higher value of current. Then the value of voltage was increased if the value of capacitance and resistance value was increased. Besides that, the value of current was influenced by the value of resistor. This is because the higher resistance value added, the value of current was decreased. So the relationship between the resistance and current was inversely proportional. Now I will explain for activity 4. The activity 4, the circuit almost same like activity 3, but activity 4 is the parallel resistive capacitive load circuits. So we use the same component and the same circuit, but this is the in parallel. Okay, so we set the value for V supply is the amplitude is 10 meter and 50 hertz, and for the both estimeter, for the ammeter, we set the power range in milliampere, and this is the voltage. Okay. By the way, we also use the different value for resistor and capacitor. Okay, now we run. Okay, we get the value. Okay, now we go to the report for activity 4, which is the parallel resistive capacitive load circuits. Like I say, in the software, in the simulation, the circuit is almost same, but for activity 3, we use the series circuit, and the activity 4, we use the parallel circuit. Okay, in the simulation, we got the simulation value for P load, and for the I in milliampere, we got for the six value of resistor and capacitor, which is here all the different value. So we got the simulation value for V and I for each value for R and C. Here we got the same, and the I, we got the different value. So this is the simulation value for the simulation that I calculate in the software. So what we need to find is the value for I in milliampere. So the calculation, we can use the formula uh, Iz equal to 1 over R plus JWC. Why we use this formula? Because we need to find the value for Z. So we use this formula, which is the W. The value for W is 2 pi F, and which is the F is 50 hertz. So here we got for the the value for Z for to for the resistor for 390 ohm and 2 microfarad, and this is the value. And do the same step for this value, this different value for the Z. So um yes. So what we can conclude in the activity 4 is for this activity 4, figure 8.4 and table 8.4 show the result from simulation. Okay, in the parallel RC circuit, the value for current and voltage in simulation and calculated was different. For simulation, we get 7.07 volt for voltage load, while calculation we use the voltage supply that given, which is 10 volt. Okay, next, capacitance value was directly proportional with the value of current, because the more value added to capacitance, the higher value of current. So the value of current was influenced by the value of resistance. It is because the higher resistance value added, so the value of current will decrease. Alright, I think that all from me for activity 3 and 4. Thank you.